So how do we get from one state to the other? And the quick answer is the energy changes. We can add energy and go from solid to liquid to gas to plasma. We can take energy away and we can go the opposite direction from plasma to gas to liquid to solid. And we change the temperature by changing the energy. So we add energy, the temperature changes. And remember that temperature is a measure of the average kinetic energy of the substances. And so as we're increasing the energy, we're increasing the average kinetic energy of the substance. And if we look at these changes of state, these phase changes, whether it's melting, boiling, evaporation, condensation, we notice that with pure substances, particularly crystalline substances, they happen at specific temperatures. And these specific temperatures are properties of those substances. And we can explain this by looking at the microscopic behavior at these particular phase changes. When we're heating the solid, so let's start at a solid phase, when we're heating it, we're giving them more and more kinetic energy. And so those molecules are starting to vibrate back and forth faster and faster and faster. The only type of kinetic energy they have is that vibrational, and so they're vibrating back and forth faster and faster until at some point they're vibrating with enough energy that they can start to overcome those intermolecular forces and they can break away from their fixed positions. And so now they start to slip and slide around each other. They're vibrating back and forth, so the distance, the average distance between the particles is increasing, and so their potential energy is increasing. And since energy always tends to flow from higher energy to lower energy, the general flow of the energy is towards the molecules or atoms that have the lowest energy, so the colder molecules, if you want to say. And so what this does is that it causes all of the molecules in a substance to change phase before the temperature starts to increase again. And what we then see is as we're adding energy to those particles and they're starting to spread apart, they're starting to separate from each other, the potential energy of the system is increasing. And if that's increasing the potential energy of the system, then it's not increasing the kinetic energy of the system. And think about what that means for the temperature, because temperature is the measure of the average kinetic energy. If the kinetic energy isn't changing, then the temperature is not changing. And we see this anytime there's a phase change, the temperature stagnates. The temperature stops changing until that phase change has completely occurred. Now, once the solid is completely converted to a liquid, now that energy starts to go into increasing the kinetic energy of the substance, and we see the temperature of the liquid now increased. And now that we're in a liquid state, that kinetic energy is in the form of both vibrational and rotational and translational. So now we have three different forms of kinetic energy in the liquid state. And that temperature increases, that kinetic energy increases until we reach the boiling point. And again, the boiling point is a specific temperature for a specific substance. So it's one of those properties that we can use to distinguish substances. And at that temperature, at that average kinetic energy, now the particles have enough kinetic energy that they can start to completely overcome those intermolecular forces and completely separate from the other particles. Now, those intermolecular forces are still existent, they're still there, but the particles have enough kinetic energy to overcome them, and so they're completely splitting apart, they're separating from each other. But because those forces are still there, that's why there's such an increase in the potential energy. It's, again, the same reason why when you raise an object higher above the earth, the potential energy increases. It's because those forces are still acting, but now they're over a greater distance, increasing the potential energy. And similar to our solid to liquid phase change, when the liquid is turning into a gas, only the potential energy is changing. The kinetic energy stays the same, and so the temperature stays the same. And this continues until the entire sample is a gas, and then the temperature will rise again. Now I'm sure you recognize our phase change diagram, and so let's just talk about this a little bit. Notice that this is specific for water, and so the temperatures on here are specific for water. They'd be different for another substance. But if we start down here in the solid phase, and it's not on here, but our label for our x-axis should be energy in joules or kilojoules. We start out as a solid, which is ice, and notice our temperature is in Kelvin, so let's assume we start down at 0 Kelvin, absolute zero. The temperature is going to increase until it gets to 273 Kelvin, 0 Celsius, which is the melting point. As we continue to add thermal energy, notice that the temperature line levels out, it flattens out, it doesn't change. And this represents that period of time when the phase is changing. At this point, it's completely turned into a liquid, and you see the temperature start to rise again. This amount of energy here that it takes to completely change the solid to a liquid is what we call the heat of fusion. Then we continue to add energy in the liquid phase. The temperature rises until we get to the boiling point, which for water is 373 Kelvin or 100 degrees Celsius. And then again, you see that the temperature levels off and stops changing. This is where we're going from liquid to steam or liquid to gas. And this is our heat of vaporization, or our latent heat of vaporization. And notice that it's much, much larger than our heat of fusion. And you think about what's going on. Here, when we're going from a liquid to a gas, you have to completely overcome those intermolecular forces. When we're going from a solid to a liquid, we're just kind of breaking those bonds a little bit, starting to move around. But here, we're completely overcoming those forces, and so it takes a much larger amount of energy to do that. And although we're not going to use it anymore because we're going to use kilojoules, in the English system, in calories, the heat of vaporization is 540 calories per gram. The heat of fusion is 80. So 7 times more energy to convert the same amount of water from a solid to a liquid than to a liquid to a gas. And then again, once we reach completely a gas, the temperature starts to go up again. And also understand that even though we're reading this from left to right and talking about energy, if we go from right to left and we start taking away energy, the reverse process occurs. And so we have to take away 540 calories per gram to turn steam back into liquid water. We have to take away 80 calories per gram to turn water back into ice at 0 degrees Celsius. So either way, it's just a matter of adding or taking away energy. So our different phase changes. Solid to liquid is melting. Liquid to gas, vaporization, we can call it boiling. If we go the other way, gas to liquid is condensation. Liquid to solid is freezing or solidification. We'll use the term freezing, but don't get caught in thinking that we're just going water to ice, that it has to be cold. The freezing point for something like lead is a very high temperature. There are some alternatives. We can go directly from a solid to a gas, and that's called sublimation. That's what dry ice does, it's what mothballs do, it's what iodine crystals do. And then if we go the other way, if we go from gas to solid, that's called deposition. Now there's one other type of phase change that we see every day that doesn't really fall into the categories that we just talked about, and that's evaporation. And the process of evaporation is when we go from a liquid to a gas at temperatures that are below the boiling point. In order to understand how or why this happens, we again have to kind of think about the kinetic theory of matter. And remember something that we mentioned earlier. The temperature of a substance is simply a measure of the average kinetic energy, but that if we look at the kinetic energy of individual particles, it's actually quite a large range. And so if we look at a graph of actual kinetic energies in a fluid, the distribution looks something like this. And the red line represents a sample of a liquid at 20 degrees Celsius. The blue line represents it at 15 degrees Celsius. And the dashed lines represent the average kinetic energy, and then the solid lines represent the actual energies of the individual particles. And so you can see that there's kind of a peak generally shifted to the left of the average, but then you also have, if you look down in the bottom right, you have a section where there are some particles that have much higher energies. And the shaded part represents what we call the escape energy. And this is the amount of energy that a molecule or a particle has to have in order to break free from the surface of the sample. And if a particle is at the surface and it has that amount of energy, it could theoretically break off the surface and escape into the atmosphere. So in order for a particle in a liquid to do that, it has to first have that amount of energy. Secondly, it has to be at the surface, and then it has to be moving in the right direction. And if all those things occur, then that particle will break off and will escape into the atmosphere and become a gas. So if we think about a puddle of water, and we think about that puddle of water on a warm day, it might have an average temperature of 25 degrees Celsius. And so there's going to be some amount of particles that have the energy to escape. Over time, those particles will make their way to the surface and they'll escape into the atmosphere. When those very high energy particles escape into the atmosphere, what's that going to do to the overall average kinetic energy of the sample? Well, if the high energy particles leave, the overall average is going to decrease. If the average kinetic energy decreases, that's going to result in a decrease in temperature, which will cause the liquid temperature to be lower than the atmospheric temperature. And so now you have a net flow of energy from higher energy to low energy. So thermal energy from the air will flow into the liquid. That's going to bring the average temperature back up. So now you have more particles that have escape energy, and they're going to escape. And it's just this cycle. This is why even in the winter, when it's cold out, puddles are going to eventually evaporate, because those particles are eventually going to gain enough energy. There's going to be particles in that sample that have the escape energy, and they'll very slowly escape, and gradually that puddle is going to evaporate. But it also explains why the evaporation occurs so much more quickly on a hot day than on a cold day, because in a hot day there are so many more particles that have that escape energy, they're going to escape much faster. And the difference here between evaporation and boiling is that when we're talking about a substance boiling, the molecules can come from anywhere, because all of those particles have enough or most of the particles have enough energy. When we're talking about evaporation, it only occurs at the surface. And this also explains why sweating carries away energy or cools us off, because the sweat on the surface of our skin is carrying away the energy. It's evaporating, it's taking away energy from our body. And so when you sweat, the water is actually taking thermal energy from your body and using that energy to evaporate, and that's dropping the temperature of the sweat, which then absorbs more energy from your body, and so there's a net loss of thermal energy from your body. Now let's talk a little bit about these terms, latent heat of fusion and vaporization, that we use when we're looking at the graph. The latent heat is the amount of energy that it takes to cause a phase change. And it's called latent heat because, remember, during that phase change, the energy that changes is the potential energy, and so there's no change in the actual temperature. That's where the term latent heat comes from. So if we're a little bit more specific, and we call it the latent heat of the specific latent heat of transformation, and we'll talk about the specific transformations. It's the quantity of energy that it takes to change 1 kilogram of a substance from one phase to another without a change in temperature. And so because there's no change in temperature, our units are simply energy per unit mass, or joules per kilogram. And our two specific latent heats are the latent heat of fusion, which is the energy it takes to convert a kilogram of a solid to a kilogram of a liquid, and the latent heat of vaporization, which is the amount of energy it takes to convert a liquid to a gas. And we symbolize those with L subscript F for latent heat of fusion and L subscript V for latent heat of vaporization. And then our equations, because that energy, or because that measurement is energy per unit mass, if we rearrange it a little bit and solve for energy, we get Q equals mLF or Q equals mLV. And we're going to be using both of our equations, our MC delta T and our ML equations, in some practice here in the near future and for our lab.